All right, let's look at reactions of amides. So amides are one of our least reactive functional groups. They're a little bit more reactive than nitriles, but generally on par with the slower end of the scale. They require activation or strong nucleophiles. So if we have a direct nucleophile addition, it's got to be a good one. We're going to have to heat because we're even less reactive than carboxylic acids and esters. And if we're using a weak nucleophile like water, we're going to have acid activation. Generally, the byproducts will kick off an amine or ammonium, or ammonia and an ammonium salt. So we have two general trends. We'll see some variations from that. Okay, so the reason for this lack of reactivity partly is due to the thermodynamic stability of the bonding in amides, but also due to a higher degree of electron density on the carbonyl carbon. So if we look first at our most reactive functional groups in the carboxylic acid derivatives, the acid halides and anhydrides can react with weak nucleophiles without activation. So these are your most active. They can react with good nucleophiles, they can react with weak nucleophiles without needing proton activation or basic, conditions involving protonation of the carbonyl. Now, if we look at esters and carboxylic acids up next, they typically will require a good nucleophile or basic conditions with a good nucleophile or acid activation. Don't always require heating. Heating will accelerate the reactions, but when we get to amides and nitriles and carboxylates, we're going to need everything we can get, the good nucleophile or the acid activation, and a high degree of heating typically to push these things through. And again, for the amide functional group, this resonance contributor that ties up the lone pair on nitrogen actually makes this oxygen the best nucleophile in this functional group. So we're going to take advantage of that resonance contributor in a later reaction. Okay, but that resonance also increases the electron density around the carbonyl here, making it less attractive to a nucleophile. All right, so let's look at reactions that form amides. And we can start from carboxylic acids by reacting with an amine or ammonium, either a primary or secondary amine and ammonia here, and that creates an ammonium carboxylate salt, which will be able to be heated and then blow off water as a thermal rearrangement here and create our amide. All right. Now, another method more commonly used, so that method's not the best in the world for preparative synthesis, but aminolysis of an acid halide, on the other hand, is more common. And so what we'll see is two equivalents of amine, because one of them is going to be tied up with a protonation, a deprotonation step in the mechanism discussed in the acid halides video. So a little bit of excess amine won't hurt here to get this reaction to go all the way to completion. We substitute the halide for an amine or ammonium. Acid anhydride will do virtually the same reaction. So we'll have a nucleophilic attack again on one of these carbonyl carbons, tetrahedral intermediate forms, then kicks off the leaving group in the next step. Proton transfer may or may not occur, discussed in the acid anhydrides video here. Okay, and so we can form an amide in this way with byproduct of an ammonium carboxylate salt. Esters, also aminolysis. Aminolysis just being cleavage with an amine, and so that's what we are discussing here. Esters may be cleaved with either neutral conditions, or I guess slightly basic, considering the basic lone pair on nitrogen. So we can take our ammonia or amine and heat this reaction to eliminate a methanol, again discussed in the esters video. And we can also use acid catalyzed activation. We don't want to put too much acid lest we protonate our nucleophile, but a little bit will go a long way toward accelerating the reaction. And so we can form our amide in that fashion as well from an ester, ammonia, and a primary or secondary amine. Now, reactions of amides, so as a reactant, we will have hydrolysis, just like all our functional groups. In the carboxylic acid derivative family, we can do hydrolysis back to a carboxylic acid. And so mechanistically, we would need to activate the carbonyl first because we have a weak nucleophile. So I'll use hydronium here as our source of our proton. And then we have an activated carbonyl, so even a weak nucleophile can add, and that's exactly what happens here, to form our tetrahedral intermediate, the first one of several. Now, as we look at this one, the best leaving group is the nucleophile we just added, so we're going to need to deactivate that using a solvent molecule here. For each of these, we could also say base from solution, so I don't mind you saying HB plus here, or base from solution for that. It's perfectly fine. Odds are it's the solvent, so we're going to stick with that for the rest of this mechanism. And our next tetrahedral intermediate has no good leaving group. Okay, so this one, we either have to eliminate an amide salt or an amide ion there, or we've got to kick off a hydroxide. So neither one of those are great options. So let's activate our amine here with hydronium. Lone pair on nitrogen grabs that proton, and now we do have a good leaving group. We've got NH3 plus, and so it's not the best leaving group in the world, so that's where the heat comes in to push through this rate limiting step. Carbonyl reforms, kicks off the leaving group, and we form our carboxylic acid protonated. And what makes this irreversible is then a very potent acid-base reaction between the strong acid protonated carboxylic acid and our formed ammonium here, or amine if we use a primary amine, a secondary amide or tertiary amide. And so irreversibly then we get our carboxylic acid and ammonium back in the end. Okay. Now in basic conditions, we're going to see a different mechanism at work. We can use aqueous hydroxide and heat this thing to form a carboxylate and ammonia. And if we do that, we've got a good nucleophile. So we don't need to activate the carbonyl. Attack, kick up the O-. Right now, looking at these two, we've got no good leaving group. Okay, hydroxide and amide are not that great of a leaving group. And so I'm going to highlight this bond to hydrogen here and show a second deprotonation to the dianion. While there is no great leaving group, the best leaving group is to kick off NH2- as opposed to O2-. Oxide ions, a horrendous leaving group. And so one of these reforms a carbonyl, kicks off the amide group, rate limiting step, slowest step here, we get our carboxylate. But amide's a good nucleophile. Okay, so we end up having an irreversible step that will protonate this. pK of water is about 15.7, and then pK of ammonia is in the 30s. So that's a huge difference in pKa. This is a very efficient transfer at the end, which locks us into place here at our carboxylate. With esterification, basic conditions will not work for us, because when we get to this intermediate, we cannot accomplish the second deprotonation. So there's no way to get that carbon group off of oxygen by means, simple means that we know. And so this isn't a very good reaction for basic conditions, but in acidic conditions we can certainly do esterification of an amide. We have a weak nucleophile, so we are going to have to activate the carbonyl first. And I will use generic base. It is protonated alcohol, okay, but we'll keep it basic, or excuse me, poor term there, keep it simple. We're in acidic conditions, so we need that +1 formal charge on our base, okay. Again, it's representing the protonated alcohol here. Okay, proceeding. We've activated our carbonyl. So now even a weak nucleophile can add, and instead of water, we want to keep water out of this system actually, because we would get hydrolysis if water were present. So let's use our alcohol nucleophile to attack the carbonyl and create our first tetrahedral intermediate. Our best leaving group is what we just added, so we're going to have to deactivate that protonated alcohol. Now we have no good leaving group, so you're seeing the similarities with amide hydrolysis here. So we're going to have to activate our leaving group on the nitrogen here by protonation. Amines aren't the best leaving group, so that's why we've got to heat this thing through this rate limiting step. Carbonyl reforms, kicks off the leaving group. We now have a protonated ester, which undergoes a fast reaction with our leaving group here, ammonia, or an amine if we're kicking off from a secondary amide or a tertiary amide. And that fast irreversible step at the end. So this is still reversible to this point, but once we protonate to form ammonium, we are irreversible. And we've got our ester in the final step, byproduct of ammonium. Alright, so we can also form a nitrile from amides, and we do that by treating it with thionyl chloride. And so the first thing we're going to look at is how we want to start this mechanism, because oxygen's actually the most nucleophilic position, and the reason is, as we said before at the beginning of the video, was this resonance contributor, which I'll indicate here by a double-sided arrow as appropriate for resonance contributors. This contributor is significant. There's a lot of negative charge buildup on that oxygen because oxygen is more electronegative than nitrogen. It would prefer to have more electron density than nitrogen. So we show that contributor, and then we get started with our mechanism. So thionyl chloride is tetrahedral. It's got that lone pair. People don't typically draw it in. Don't forget it is there. And so it can undergo a direct SN2 reaction here from oxygen, kicking off one of these chlorides. At this point, we can have a base from solution remove this proton, creating an unstable intermediate. Up to this point, we're fairly reversible still. But this unstable intermediate will form the triple bond that we need, break the carbon-oxygen bond, form the sulfur-oxygen double bond, and kick off a chloride, irreversibly forming our protonated nitrile and giving off a byproduct of SO2 gas, which drives this by Le Chatelier's principle, removal of a product, very high gain of entropy in this step, and so we find that it goes irreversibly, and then finally we'll have that base from solution, a lone pair capable of grabbing a proton, forming our nitrile in the last step. Okay, and so reactions of amides, fairly pedestrian list there, but we do have one more that's a little bit different, reductions with lithium aluminum hydride. And our amide's going to form an amine. If it's a primary amide, it forms this primary amine. If it's a secondary amide, we would end up forming a secondary amine. Okay, we've been saying that a couple times just to kind of define that out. If it is a tertiary amide, tertiary amine. All right, so let's look at the mechanism of lithium aluminum hydride reduction. It's very similar to the reduction of a carboxylic acid. The reason is we've got these acidic protons here on nitrogen, and so if we take our hydride, aluminum is a column 3 element. It has 3 valence electrons. In this particular Lewis structure, it has an octet, but formal charge wise, that gives it a -1 formal charge. So to get rid of that formal charge, donates a hydride commonly, and the bond nitrogen to hydrogen then breaks, then kicks up a lone pair onto oxygen after forming a carbon-nitrogen double bond. So the net result of this step is an irreversible addition of a hydride that creates, an acid-base reaction, getting ahead of myself there, that creates a carbon-nitrogen double bond and eliminates H2 gas irreversibly here. Also creates aluminum hydride. So now we have a neutral formal charge. This is isoelectronic with BH3, so we can think kind of like hydroboration here. That aluminum is electron deficient and it wants a lone pair. The best option is that oxygen that we just kicked up the negative charge to. All right, and so that complex, this is a Lewis acid adduct, and it still has these hydrogens attached, and so one of them is in, at any given time, is in the correct proximity to donate to the CN double bond and kick that up to a negatively charged nitrogen. Now we've got our tetrahedral intermediate. And this structure will then reform a carbon-nitrogen double bond, kicking off OALH2 as a leaving group. This gives us our functional group, the imine. And imines are reduced by hydride reducing agents, just like ketones and aldehydes, by addition of a hydride to the CN imine carbon there, the CN double bond carbon. We kick up to a negative charge on nitrogen here, just like we would if it were carbon-oxygen double bond. But at this point, our tetrahedral intermediate does not have a leaving group, and so we are stuck until we add, in step 2 of the mechanism, some water. We add water because nitrogen, negatively charged, is so basic that it can deprotonate water to form hydroxide very efficiently, and that gives us our amine. If we'd used hydronium, we would end up protonating this amine, which is sometimes desirable, but in this case we want the amine product, so we will use water as the workup to keep that proton off.